Hi again. On this video, we'll be covering chapters 2 and 3, just the highlights as I talked about in the last video. These are chapters on probability and statistics, and it should be a review of one of the prerequisites we have for this course. So I'm just going to try to hit the highlights. Even so, it's going to take a little while to get through some of the material. There's a much more detailed discussion of all these topics in the book. And so if you need more than I'm going to present here, I encourage you to go ahead and read both chapters 2 and 3. As I said last time, if you're very familiar with this material, just had this in math and you know it, you probably don't need to do much with those two chapters, but I'm going to leave that up to you. Probably do a lot on probability, not quite as much on statistics now on hypothesis testing, because I want to save some of that material for when we actually get to regression models. It's the same material and I don't want to duplicate it, no sense doing it twice. And so I might save some of the statistical part until we get to chapter 4. Okay, so let's look at probability, random variables, and distributions to begin with. Probability, random variables, and distributions. I'm not sure if I got all that on the video, but anyway, this says probability, random variables, and distributions. So let's start with a random variable. A random variable, which I'll often abbreviate as RV, or sometimes they're called a stochastic variable. Stochastic just means random. Is a variable whose value is a real number. It could be continuous or discrete, determined by the outcome of an experiment. And sometimes we perform those experiments in the lab. Sometimes nature performs them for us, so nature might put out random variables through some sort of what we call natural experiment. So for instance, for example, a coin toss. That's the experiment, is the experiment, and then a head or a tail is what we call the outcome of the experiment. And what we might say is if it's a head, then we're going to assign it a value equal to 1. If it's a tail, then we'll assign it a value equal to 0. So in this case, 0 and 1 are the random variables. And it wouldn't have to be 1 and 0. We could assign whatever numbers we wanted, 1 and 2, whatever. We just assign it some number based on the outcome of the experiment, and we assign it those numbers. Those turn out to be the random variables. Random variables aren't letters like H and T. Remember, it's a real number. And so we make these assignments to give us a random variable. Sometimes, like if you spin a wheel and it's got numbers on the outside like a roulette wheel, then the outcome is automatically a number immediately. You don't have to make these kinds of assignments. But if you had letters around the wheel, you'd want to assign a number of some sort to each one so that the outcome of the experiment was a random variable. And then there's two main types of random variables, continuous and discrete. And those just have the normal meanings of continuous and discrete in mathematics. So a random variable is continuous if it can take on any value in a continuous interval. One type of a probability distribution is a uniform distribution. So it might go, the example I'm going to use later, that goes from 0 to 4. And the height of this might be 1/4. So what we're saying is this random variable can take on any value between 0 and 4. And the probability basically of any value is 1/4 of any one of these. And then if we look at the total area of this, it's just this times this. The total probability is 1. And so the height of this thing is basically the probability of a particular outcome. And if we sum the probabilities times the outcomes, then we get 1/4 times 4, and you get a total probability of 1. So later on, we'll talk about probability density functions in a minute. This is just an example. The idea here, though, is this is a continuous random variable. You know, you could have an outcome that's 2.1783, or any number. I just made that up. And so a continuous random variable takes on any value. A random variable is discrete. We just did a discrete one, or it could only take on, with heads and tails, 0 or 1. It couldn't take on any value between 0 and 1, so it's not continuous. If it can only take certain values. So the roll of a dice is a discrete random variable because the outcomes, the random variables are 1 through 6. You can't have anything between those things. Okay. Let's next talk about the cumulative distribution function for a random variable. So what is the cumulative distribution function? And we use a capital F in probability and statistics to represent cumulative distributions. Something that's related that you should have seen is called a probability distribution. This is a CDF, a PDF, a probability distribution function, will be a small f. It's actually the derivative of this thing under most conditions, and we'll come to that in a second. But f of x is just the probability that the random variable, whatever it is, so the random variable here is x, is less than or equal to some value x. So if I roll a die, I could talk about the probability that the outcome was less than or equal to 3. The probability of that would be 1/2. The probability of a 1, 2, or a 3 would be 1/2. And so it's a cumulative probability function. You could talk about the probability that the random variable was less than or equal to 5, which would be 5/6 in that example. And so that's the definition of a CDF. It just tells us the probability that a random variable is less than or equal to a certain value. If it's differentiable, and most of the time it would be, we're not going to ever look at anything in here that isn't, that I can think of, then f prime x equals f of x. This is what I was saying before. The derivative of this thing with respect to x is the probability distribution function. And again, this is often called the PDF. This one's often called the CDF, the cumulative distribution function. If it's discrete, the PDF, f of x, is just the probability that x equals some outcome x. So the capital letter here, the bigger letter, is the random variable, and this is some specific value. So again, like I was just saying with the die, you could look at the probability that x equals 3, which would be 1/6, or the probability that x equals 1, which would be 1/6. So in the discrete case, it's just the probability that the random variable takes on one of those discrete values. For a continuous random variable, you have to be a little bit more careful. in specifying exactly what it means. But if it's continuous, then we know several things. First, that f of x is greater than or equal to 0. Probabilities can't be negative. The same thing's true here. I didn't say that. That would also be a property. The second thing is the area underneath the PDF. So if I integrate over the whole area, f of x, dx, I'll get 1. The same thing would be true if I sum over all the possible outcomes. The total probability has to be 1. The probability of 1 is 1/6, 2 is 1/6, the probability of a 6 is 1/6. If I add up 1/6 6 times, I'll get a total probability of 1. And so when you sum over all the outcomes times the probabilities, you get not times the probability, you just sum over all the outcomes, you'll get a probability of 1. Same thing's here. And then the third thing, which really is how you usually use these, is the probability that the integral of f of x dx between a and b, so I don't know if you can see that, but the limits of this integral are a and b, of f of x dx, we're just integrating the PDF. That's the probability that a is less than or equal to some value x is less than or equal to b. Sorry, that's the capital, that's the random variable. So it's the probability that the random variable ends up somewhere between a and b. So let me spend a little more time on this, making sure you have these properties. Normally in a regular class, when I have people out there, I can watch them and see when they're writing furiously. I tend to slow down, let them catch up. When they're looking bored, you can kind of speed up a little bit because it looks like they're getting it, and sometimes faces are hard to read, but you can sure tell when people are scribbling furiously and need you a little more time to catch up. You naturally pause because you can see that. People ask questions, try to slow you down, those sorts of things. Here, I don't have the ability to look at you and see if you're scribbling furiously, but what you can do that a class can't do is put me on pause. And you can even rewind the video a little bit. So I'm just going to plow on in these videos. If you need time to catch up, because you don't get it in your notes, just hit the pause button. If you miss something, unlike in a class, you can go back and run that again. And so even though I'm going to go a little faster, it should be even better than it would be in a regular class. And then if you have questions, we'll have to handle that a different way. But in any case, don't hesitate to pause these things if you need to. And if you missed something, you didn't quite get it, go back and watch it again. Have your book there, put it on pause, read it in the book, then go on in the lecture or something like that. And so hopefully this works even better, but we shall see. If you were to take a normal distribution, and you remember what those look like? We'll talk a little more about normals later. They look like this. This tail doesn't actually go to 0 until you get to minus infinity or plus infinity. It's centered on somewhere. Some mean, mu, is the symbol we use for the mean. So this is the random variable x, and it can take up on any of these outcomes. This is a picture of the PDF, the probability density function. And so what those three properties we just wrote down tell us is that, first of all, it's always positive. We can't have negative probability. And so the probability of any one of these things is always going to be positive. So it's always above 0. The second property was that if we integrate over this whole thing, the total area underneath this curve has to be 1. And the third property was that what it tells us, if we have two limits here, A and B, then the area under here, if we take that area in this range, so the area under the curve between A and B, that's the probability that the random variable x is between those two values. We can't define it at a single point because that width is 0. We get a 0. It doesn't work for a single point because it's continuous. But we can define probabilities this way. So we can use the PDF to look at these kinds of probabilities. What the CDF is, so I'm going to use the same example here. We're going to have a normal distribution centered at the mean u. The CDF takes some value here, little x. Maybe this is 10 or something like that. So this is some number. The CDF is this probability. It's the probability that the random variable x is less than or equal to this particular value. So it's the area underneath the curve up to this point. So what the CDF for a normal would look like so here's the random variable x. The CDF for a normal looks something like this. And I didn't draw that very well. It should be more of a slope here initially. Let me just try it again. I'm not the greatest artist who ever lived, but I'll do my best. And so it starts off and rises and eventually asymptotes at a value of 1.0. So if I were to look at the height here, here's the mean. This height eventually gets to 1.0 because the probability, as I get out here to infinity, the probability that the random variable x is less than infinity is 1. It has to be somewhere in that range. And so what this is if I just take this x here, this value is the area under that curve. It's the probability that x is less than or equal to x. Now at u, the probability that x is less than u, this is symmetric. This has to be 1/2 right here for a symmetric distribution like this, because the area under here is equal on both sides. So the probability that x is less or equal to u has to be 1/2. So the area up to the midpoint is 1/2. And so this cumulative, the cumulative adds up all the probabilities up to that point has to be 1/2. When I get out to infinity, so the CDF has to have a value of 1.0, and this is the PDF. Again, these are for normals. For other random variables, they're going to look quite different. The most widely used PDF is the normal. So let me go on to that. I forgot to look at the time when I started to see. Oh, I've got it right there. Okay. So the most widely used is the normal. And we're not going to need to know this too much, but the PDF for a normal is 1 over sigma. Sigma is the standard error, square root of 2 pi, e to the minus x minus mu. That's that mean I wrote down that was in the middle, squared over 2 sigma squared. So that's the equation of a normal PDF, is this thing. So I just give it, I know the mean, I give it an x, and it gives me the height at that point. So what this tells me is here's mu, the midpoint, this thing here. What this is that at any x, it gives me the height of the curve. So I just plug an x in there. I know what mu is. I give it an x, and it tells me what the height of this curve is. And then I can integrate this thing to get, say I want the CDF for this little x. I need the area up to this point. I could integrate up to that point to get the CDF. And we'll be using the normal almost exclusively for hypothesis testing. You probably looked a lot at t-tests. there's a t-distribution and a normal distribution, and you use the t for really small n's. We're going to rely on large sample properties. The t-distribution converges to the normal when n gets big, and we're going to use that property mostly to use the normal distribution to do our hypothesis testing. But we'll come to that later. You may not quite have caught everything I just said, but we'll come back and cover that point again. Okay, good enough. Let's talk next about mathematical expectations. The mean and the variance. So the expected value of x expected value of the random variable x, we write that e of x is defined as for discrete, it's the sum, let me put the ex there so you have it in your notes. The expected value of x, I'll do an example of this in a second so you can see how it works, is the sum over the outcomes, so this I is the number of outcomes, of the probability of an outcome times the outcome. So for a dice, the expected value of x would be 1/6, the probability of 1 times 1. And it'd be plus 1/6 times 2, plus 1/6 times 3, plus 1/6 times 4, plus 1/6 times 5, plus 1/6 times 6. So we take the probability of each outcome, 1, 2, 3, 4, 5, 6. So you take the sum of the probabilities times the outcomes. I think that would come out. What would that come out? It'd be the midpoint there, right? So for a dice, it'd be 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6, so that's 11, 15, 18, 21 over 6, which is 3.5. And so the expected value of this thing is not something you could ever get. You couldn't roll a 3.5, but that's, if you just assign numbers, I get $1 if I roll a 1, and I get $6 if I roll a 6, what's the average payoff? It would be $3.5 is what you would get on average. I did that right? 3, 6, 10, 16, 21, 6. 3 times 6 is 18 with 3 left over. Sounds good. Okay? Now, if it's continuous, we're still doing the expected value. We just do the continuous analog of that. So remember that EX is the integral over the range of the PDF of x, the outcomes, times their probabilities, f of x. The height of the PDF is the probability, and x is the outcome. So what we have to do is sum over infinitely small things, because the width of a line is very tiny. And so we can't add them up like the same way we can discretely. We have to integrate. But integration is just the limit of sums when the interval gets very, very tiny. And so this is just the same thing. It's a sum of the x's times the probability of the x's. And so it turns out to be the same thing intuitively. Because it's continuous, we have to do the math a little bit different. So again, for the heads and tails, if a head is a 1 and a tail is a 0, and the probability here is 1/2, and the probability here is 1/2, so this is what you get Someone says, would you like to pay 75 cents to pay this game? I'm going to flip a coin. You get nothing if it's a tail. You get $1 if it's a head. Do you want to play that game? You already know the answer because you know the average is 50 cents. You intuitively can see that. Why pay 75 cents for something you're only going to get 50 cents on average? But let's check that. The expected value of x would be the probability of a 1 times the outcome plus the probability of a 0 plus the times the outcome, which is going to be 1/2. And so you'd only get $0.50 on average from the coin toss. So why would you ever want to pay 75 cents to play this game? You could change these probabilities. You could make this, say, maybe it's an unbalanced coin. So the probability of a head is 5/6. The probability of a tail is 1/6. Then the expected value is going to be different. Now you'd want to play this game because the expected value, the average value, would be times this, 1 times 5/6 plus 0 times 1/6, which is 5/6 of a dollar, which is greater than 75 cents. And so in this case, you'd be willing to pay 75 cents. Because if you kept playing this game over and over and over, you're going to beat the house. Okay, so that's the expected value of x. Now don't let this e of x fool you. I really want to encourage you in this class to realize that these symbols are nothing more than concepts. They're trying to get some concept across. And so when you see e of x, what you should say in your head is the average value of x. That's what it's measuring. It's the mean. It's the average value. So the expected value of x is equal to the mean of x, or its average value. Remember that uniform distribution that we did earlier? Where in this case, f of x is equal to 1/4 for 0 less than or equal to x is less than or equal to 4. And what that looked like was a PDF that looked like this. So it started at 0, it ends at 4, and it has a height of 1/4. So this is the PDF for this function. For this is the PDF. Here's a picture of it. If I integrate over this whole thing, the integral from 0 to 4 of 1/4 is 1. The area of this is 1. We don't have to do integrals. We know how to do the area of this box. It's this times this. You could also do it by integrating, but we don't have to do that. But the question is, what's the expected value here? Now, I think you can see that it's got to be 2. 2 is going to be the balance point. It's going to be on average. And so if this is what your PDF looks like, these are all the possible outcomes. It's continuous, and each one has that probability, 1/4, then the average value is going to be 2. But let's check that. So for this problem, the expected value of x is going to be the integral from 0 to 4 over the range of x times, remember we said it's x, times f of x. And in this case, f of x is 1/4. So it's x times f of x. That's a pretty simple integral. That turns out to be 1/8 x squared from 0 to 4, which turns out to be 16 over 8 minus 0 over 8 equals 2. So as we thought, the expected value of this random variable would be 2, which is the midpoint of the CDF. So that's the expected value of x. It's also called the mean of x. So the mean, what we're writing u, is just the expected value of x. So we'll use both these symbols. to represent the expected value of x. The variance of x is another expected value, but it's a little different. It's the expected value of x minus the mean squared. So it's x minus the expected value of x squared. For continuous random variables, this is just equal to the integral from minus infinity to infinity over the range of x times x minus mu squared f of x. So it's the same thing, dx. Oops, earlier I might have written, I forgot my dx's. When I took calculus, my teacher really got upset if you forgot to put your dx's on there because you didn't know what you're integrating over and used to lose points, and it used to annoy me. Well, I just lost some points because I think I forgot to put some dx's on that last example, and maybe when I originally wrote it down, I'm not sure, and I apologize for that. It should be the expected value of x should be the integral of x, f of x, dx from minus infinity to infinity. This is just the expected value of x minus u squared. I can put brackets around here if it helps you. So it's the thing times the PDF is the way you get an expected value. So for continuous, the variance is defined that way. So that's equal to the variance of x. And we usually would call that sigma squared x. So the variance of x is sigma squared x. Okay? For a discrete random variable, it's a little bit different. So for a discrete case, it's the same thing. For discrete, it's just a discrete analog of the continuous. For a discrete random variable, then, the expected value of x minus the mean squared is the sum over all the outcomes. For a die, I would go from 1 to 6. For the coin toss, it'd go from 0 to 1. These are just all the discrete outcomes that we're summing over, times xi minus mu squared times the probability of I. And again, that's sigma squared x. So the definition depends upon whether we have a discrete or a continuous random variable, but intuitively it's the same thing. The expected value of anything, the expected value of triangle, the expected value of anything is anything times the probabilities summed. So, yeah, I don't think there's much more to say there. Let's do a couple of examples of calculating the variance, just so we see for sure how that works. And so, suppose the probability of a so this is the head equals 1, tails equals 0. This probability, I'm going to take the unbalanced case as 5/6, and this probability is 1/6. So this is the unbalanced coin. Now we showed already that the expected value of x is 5/6. So how do we get the variance of x? So what should the variance of x be? Sometimes I'll write this as v of x, use both symbols. What should this be? Well, remember, it's the sum over the outcomes, I equals 0 or 1, of the xi minus the mean squared times the probability of I. So what is that going to be? It's going to be, let's do 0 first, 0 minus 5/6 squared times what? Times 1/6 plus, what's the value here? The outcome is 5/6. This is actually the same as the probability. So this one's going to be 5/6 minus, remember this is the mean here, and this is the outcome. Oops, not 5/6. 1 minus 5/6 times 5/6. So this is minus 5/6 squared times 1/6 plus, and what's this one going to be? 1/6, and I forgot my squared there. Sorry about 1/6 squared times 5/6. That turns out to be 5/6 times 1/6 times 5/6 plus 1/6, which is 5/36. So the variance in this example would be 5/36. So the expected value of x is 5/6. The variance of x turns out to be 5/36. And so again, it's just a sum of, so to find a variance, first you find the expected value, then you just take the sum of the outcomes, 0 or 1, minus the expected 5/6 times the probability of each one, just like we did here. And we get an answer that turns out to be the variance. For the other example, the uniform distribution, remember the one where f of x equals 1/4 for x between 0 and 4. What's the variance in that case? Well, in this case, we showed that the expected value of x was equal to 2. So what we need is the expected value of x minus 2 squared. And we say, okay, well, that's the integral over the range of x, 0 to 4, of f of x minus 2 squared times f of x, which in this case is really simple. So that's the integral from 0 to 4 of the 1/4 times, let's just do it easy, x squared minus 4x plus 4. And I forgot my dx again. Dx. And so that's x cubed over 12 evaluated from 0 to 4 minus 2 over 4x squared evaluated from 0 to 4 plus 1/4 and 4th cancel. So we just get x evaluated from 0 to 4. So this is 64/12 minus 8 plus 4. And when you work this all out, you get 4/3. So the variance in this case turns out to be 4/3. The square root of the variance is the standard deviation. And that'll be a very, very useful thing for us. So if I take sigma squared and I take its square root, I get sigma, and that's called the standard deviation. Let me just jump ahead a little bit and just tell you where we're headed with some of this stuff so that we don't, so we know what we're going to do. Remember how you did a t-statistic, which was equal to the estimated value, so you minus the hypothesized over sigma. And what we wanted to know is, so the null here might be that some random variable x equals the hypothesized value. This might be 10, okay? And so that might be, maybe we want to look at, so we say, okay, we think x is 10, and the alternative hypothesis is x is not equal to the hypothesized value. In this case, it's 10. Then we estimate a value of 12 what we want to know is, because our estimate's going to be noisy, we're going to sample from some population. So we're going to say, okay, of all of the people in the world, what's their average height? And so we sample 2,000 people. That's not everyone in the world, and we measure their average height. That's not going to be exactly equal to the true population mean, the true population average. And the question is, though, if we say, well, we think the average height is 5'5", is that close enough to 5'5" that we can say, yeah, it looks like our hypothesis is correct, because we're going to get some noise, because we're just taking a sample. Sometimes when we estimate this, we'll get 5'7", sometimes we'll get 5'5", sometimes we'll get 5'4", maybe we get a really weird sample and it's even shorter or larger. There's some distribution each time we sample. So we take 2,000 people, calculate the mean, we get, it's just like if you, flip a coin 10 times, on average, you're not going to get a half. You might get 8 heads and 2 tails one time. Another time, you might get 2 heads and 8 tails. And sometimes you get 6 and 4, and 4 and 6, and 5 and 5, and maybe even sometimes 10 and 0. If you get a really, really weird outcome where you just, wow, head. There's some probability that's going to happen. So if we were to say that we know the true value is a half, but any sample that we measure, we might get 6 heads and 4 tails, then we're going to measure the mean as 3/5 in our sample, because we'll have 6 ones and 4 zeros, and 6 over 10 would be 3/5. That's not a half. Given that we only took a sample of 10, such a small sample, is that close enough to 10 to be, to say, yeah, or close enough to a half? So we measure 3/5. Is that close enough to a half to say we can't reject that in the true population it really would be a half? You see what I'm saying? So we take this sample. If we flip the coin an infinite number of times, we'd get a half if we average everything. We know that from the law of large numbers. But if we take a sample of only 10, we could get all sorts of things. And so is the coin balanced? Is it true that the probability is equal to a half? Or is it maybe unbalanced? Well, if we get 9 heads and only 1 tail, we're likely to think we have an unbalanced coin, because in a single 10 flips, that's very unlikely. If we get 6 heads and 4 tails, and we only took a sample of 10, that's not far enough away to say, nah, it's probably not true that thing's equal to a half, because we only took a sample of 10. Now, if we took a sample of 20,000 and we got that far away, maybe that's far enough away to conclude that it's not equal. But with a small sample like that, So what we need to do, so we might have an estimated value which is 3/5, or I did 12. It doesn't make any difference. But what I'm just talking about, this would be 3/5, and this would be 1/2. Is that difference big enough to reject that this is equal to that the actual mean? So this is what we estimate from the population. Is this big enough to say, no, it's probably an unbalanced coin. It's probably not equal to 1/2. Or what if this were 9/10? We got 9 heads and only 1 tail. Is it a balanced coin? You might be thinking, boy, I don't think so. That's really unlikely. It looks like a head is far more likely than a tail. Maybe this is just a weirdest sample, but and if I did this again and again and I kept getting 9/10, you'd be pretty sure it was unbalanced. And so the way we're going to be able to tell that is we're going to look at the standard error. If we divide by this, suppose that I do the original example, suppose that this is 12 and this is 10, and our standard error is 0.5. So that's how far away this ought to be on average in some sense. So if we get, so this is the standard deviation, the standard difference, the sort of the expected difference between these two numbers. That's a normal difference. Well, this would be this would turn out to be 4.0. That means this is 4 standard deviations away from. The one we estimated is 4 standard deviations away from the hypothesized value. That turns out to be a long, long way. And you probably would, in a case like that, say, no, those two numbers aren't equal, because it's so many standard deviations away. So all this test statistic is is the number of standard deviations you are away from the hypothesized value. And when you get a long, long way away, you're more likely to think that the population mean is not equal to the hypothesized mean because your sample mean is so far away from what you thought. And so if this were, say, 2.0, say it's 2.0, then this is 1. We're only 1 standard deviation away from the hypothesized value. In statistics, that turns out to be pretty close. In that case, we probably wouldn't think that these two things are different. So we're going to use these variances to figure out how far away we are from the hypothesized value. So we'll say we think the population mean of this distribution is 10. We measure the population mean and we get a 12. So we say we think it's 10. We measure it through a sample and we get a 12. Is 12 far enough away from 10 to reject? And the way we answer that question is by comparing it to how far away we are on average. And so if the standard deviation is 2, we say, nah, that's pretty close. We're just 1 standard deviation away. If the standard deviation is 0.25 and we're 8 standard deviations away, we're thinking, man, that's a long way. On average, we ought to be sort of within 10.25 or plus or minus 2 standard deviations is sort of a normal interval. So we ought to be like between 9.5 and 10.5 if the true mean was 10. We're nowhere in that range. That's too far away given how far we expect to be away on average. So we're going to reject the hypothesis that it's equal to 10. So that's where we're headed with all this stuff. That's why we're going through all this stuff. So we can use these means and standard errors and things to do hypothesis testing. Okay. So far, we have done expected values, the mean, and the variance for single random variables. In a second, we're going to go on to multiple random variables. But I want to do one more thing first. We've basically looked at the expected value of x. That's called the first moment of a probability distribution. The expected value of x squared, and we can get this is related to the variance. That's called the second moment. It's basically the variance, but we have to subtract off means to get to the variance. But this is called the second moment. You can also talk about the expected value of x to the r power, and that's called the rth moment. Most of the time, we're only interested in the first 2 moments of a probability distribution. Sometimes you'd be interested in these higher order moments. For instance, the expected value of x cubed gives you something called skewness. It tells you how asymmetric a distribution is. So if a distribution looks like, say you've got a probability distribution and it's way loaded with probability on one side, so it's not symmetric, that's a skewed distribution. A normal is completely symmetric, this one isn't. And so in this case, we could use expected value of x cubed to characterize the degree of skewness. I'm not going to go through that. Your book goes through that in some detail. I'm not going to bother with it. The fourth moment, the expected value of x to the fourth, is something called kurtosis. And what it tells you is how fat the tails are. It tells you how much area is out here in the tails. And if you have a lot of kurtosis, it means really extreme values are highly likely. And when kurtosis goes down, it means that values very far away from the mean aren't very likely. And you can get some big problems if your kurtosis gets too high. We're not going to have those problems. I'm not going to worry about it. But anyway, you can define moments other than the mean, and this is related to the variance. This is the variance for a mean of 0. And so in that sense, it's a variance. But you can do these other moments as well. All right, so we've looked at what they call univariate distributions, or probability of just one random variable. We can also, and you can generalize this to more than 2, but once we get to 2, hopefully we'll see how to generalize. You can talk about bivariate distributions. And this is when two probabilities are involved. And what we're interested in here are joint distributions, marginal distributions. I'll define these in a second. Correlation, and covariance. We can also talk about the mean and the variance of these things, but we've done that already. It's really nothing new there. So when we get to these bivariate distributions, these are the new concepts we need to talk about. We already know what a mean and a variance is, and we'll show those for these as well. So, and these will be very useful, these joint probability distributions, in characterizing regression equations. And we'll see how it works. This stuff seems complicated right now. It's not going to be as bad as it probably looks. I want you to remember how many students take 320 every year. We offer it every quarter. 100 and something people take it every quarter. And almost all of those people pass the course. And so you'll get there. Just hang in there. Again, this should all be reviewed. When we get to the regression stuff, it won't be quite this statistically intense. Okay, for bivariate distributions, let me see how much time has gone by. Okay, got a little more. I'm going to try to limit the videos to around an hour. Sometimes we'll go over. I might go as long as an hour and a half. But in this case, I'm going to have to break this one in half, because I don't want to have videos that go, a couple hours, because that's just too long to watch in one sitting. So I'm going to cut this one off at about an hour. But we got a little time left, so let's keep going. So I'm going to look at the bivariates through an example. So just notation, the PDF defined over a pair of random variables x and y are known as bivariate distributions and are written as f x y of x and y. If it's discrete, f of x, y is just the probability that x takes some value. Remember the little things in actual value, and y takes some value. So for instance, in my example here, we're going to have a spinner. It has 4 sections, 1, 2, 3, 4. And we're going to spin the spinner. And we'll have 1, 2, 3, 4 as one outcome. Then we're going to spin it a second time. That's the second outcome. And the spinner is 1 through 4, the possible outcomes. We could ask, what's the probability that x equals 1 and y equals 4? Let me make sure those are yes. So what's that probability? How likely is it that when we spin it twice, we'll get a 1 on the first outcome and a 4 on the second spin? And that would be a bivariate distribution. It's 2 random variables working at once. And you could define this for 3, x, y, z, for 4, for 5, for 6. For x, y, z, you just have the probability that z equals some value. I could spin the spinner a third time. Or I could do completely unrelated things. I could have x be the outcome of the spinner, and y be the outcome of rolling a die, and z be the outcome of flipping a coin. And I could say, what's the probability that the spinner equals 1, the die equals 4, and the coin flip equals 0, or something like that. and those would be multivariate. So the generalization of a bivariate is a multivariate. But we're just worrying about bivariate because that's all we really need. So let's do that example I just talked about. So we're going to spin twice. So we've got this spinner. We've just divided it into 4. 1, 2, 3, 4. And we've got it set so it can't come out on the borders. And so we spin it, and it comes out one of these 4 numbers. Okay? So we're going to spin twice. So we have a spinner that can be 1, 2, 3, or 4. And we're going to spin twice. Let the random variable x be the number of ones, and let y be the number of 4s. So let me draw something here. I'm going to erase this. Sorry, I need more room. So we can write out all the possible outcomes. So this is the outcomes for the spinner. We could get 1 on the first one, 1 on the second, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3 on the first spin, 1 on the second, 3, 2, 3, 3, 3, 4, and 4, 1, 4, 2, 4, 3, and 4, 4. Those are all of the possible outcomes. Okay. Now, these in the middle don't have x equals 1 or y equals 4. So those are not outcomes that, well, let me show you. Let's do the PDF for this thing. So here's x, which is the number of ones, is ones. And we could get 0, 1, or 2 ones in our throws, right? And so let's put this, and here's y. And y is 4s. And again, we could get 0 4s, 1, or 2. So this is the number of 4s in both throws, and this is the number of 1s in both throws. So how many times is it likely that we're going to get no x's and no y's? No 1s and no 4s. Well, we can see there's 16 possible outcomes. So every time we spin this spinner twice, it will be one of these 16 outcomes. In 4 of those outcomes, we don't get any x's and any y's. So the probability of that is 4 over 16. It's 1/4. You see that? Then in the, how many ways are there to get 1, 1 and 0 4s? Well, let's see. Here we got, at least we got 1, 1. But we got 2 1s, so that's not it. Here we get 1, 1 and no 4s. Here we get 1, 1 and no 4s. Here we get both a 4 and a 1. So these two match because we get 1, 1 and no 4s. Here's 2. Here we get 1s and 4s. And all the others, you don't meet the condition. Because here I get at least 1 4. Here, all of these I get a 4. Okay, and so I miss 0 4s. Here I get 2 4s. That's not 0 4s. So none of those can count. And so the only ways to get here would be this one, 1, 1 and no 4s, 1, 1 and no 4s, 1, 1 and no 4s, 1, 1 and no 4s. None of the others match. So that, again, there's 4 ways out of 16 outcomes, so the probability is 1/4. Now, what's the probability of getting 2 1s? Well, there's only one way that can happen right here. There's 16 outcomes, so this is 1/16. Now, I'm going to let you, on your own, figure out some of these others, but if we were to write the numbers down, 1/4, 1/8, 0, there's no way to get 2 1s and 1/4 because we're only rolling twice. So the probability of that is 0. That's not even feasible. This one's 1/16 again because there's only one way to get 2 4s. This means 2 4s and no x's. And the other 2 are 0 because we can't get 2 4s and any x's. And so those are all 0. So that's the outcome. Now, if we sum, I'm gonna do something else here. I'm gonna put 2 more things on here. This I'm gonna write Fy of y. These are called marginal distributions. And I just add these up. If I add 4/16 with 4/16 with 1/16, I get 9/16. I'll explain these in a second. This one's 3/8, 6/16, and this is 1/16. These should sum to 1. They do. 9 plus 6 is 15. 6/16 plus 1 is 16. Sum them in this direction. I believe I get the same things. Yeah, 9/16 here. 1/8 plus 1/4 again is 3/8. And this is 1/16. And this is Fx of x. Okay. So the thing in the middle is the bivariate distribution that we were talking about. So those are all the possible outcomes that you could get, 0, 1, or 2 x's, 0, 1, or 2 y's. So those are all the possible bivariate outcomes we could get from the 2 random variables, spinning the thing twice. And these are all the probabilities. So the thing in the middle is that f of x, y of x and y that we were talking about. What these things are on the margins are just the probability of y alone. So this is, you just add these up. So if you want to know what's the probability that you'll get 0, 0 4s, and you don't care about the x's, well, the way to get 0 4s is 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 16 is the way. Here we don't care what x is. X can be anything. What's the probability of 0 4s? Well, it's 9. There's 9 ways to do that, all of those over 16. What's the probability of 1 4? Well, let's see. There's 1 4, 2, 3, 4, 5, 6 out of 16, 3/8. And the only way to get 2 4s is there, which is 1/16. So this is just the probability of y alone. Same for x. The ways to get no 1s are what? Everything except all of those on the outer border, there's only 1 x. So all the ways of getting no x's, no 1s at all, are all of those. There's 9 of those, 3, 6, 9. Those are all the ones that don't have a 1 in them. And so this probability is 9/16. So this is the probability of x alone, not caring about y. So these things are called the marginal distributions. This is the marginal distribution of x. And this is the marginal distribution of y. So you can get the marginals from the, this is the bivariate distribution. This is distribution of x and y together. Okay? That's the terminology that we're interested in. So this here, this number, this 9/16, that's just the probability that y equals 0, not caring about x. These are the probability that y equals 0 and x equals 0. This is the probability that y equals 0 and x is anything, and those are the marginals. This, for instance, is the probability that x equals 1, not caring what y is. So we sum up over all the y outcomes to get the x. This is the probability that y equals 1, not caring what x is, so we sum over the x's, and so on. So we have the joint distributions, or the bivariate distributions called the joint distribution, and we have the marginal distribution. So the joint's in the middle, the marginals are on the side, and they're related in that way. So let me be a little more precise. So I'm going to come back to this example, but I don't have a big enough board to leave it on here. Sorry about that. I'm going to have to erase it. I'll write it again when we need it. But you have it in your notes there, I hope. So you can refer to it as we need it. So these are just the definitions, okay? So given the joint distribution, so given the joint or bivariate distribution, I don't want the cumulative, I want the PDF, f x, y of x and y. Given that, then if x and y are discrete, as in the example we just did, then fx of x, the marginal distribution of x, so this is the marginal distribution of x again, is just the sum over all the y values of the fxy of x and y. So we just sum like we did in the example. We sum across a row or down a column. And fy of y, the marginal distribution of y, is the sum over the x values of the f of x, y of x and y. Remember, like if we take that first row in our example, we had, this was y over here, and this was 0, and this is x, and it could be 0, 1, and 2. And the probabilities were 1/4, 1/4, and 1/16. If we want the marginal distribution for y equals 0, a minute ago I wrote that one value was fyy. The marginal distribution is all of them. Let me do this right. 0, 1, and 2. I'm going to do exactly what I did a second ago. This is 1/4, 1/8, 0, and this is 1/16, 0, and 0. If I want fy of y, the marginal distribution of y, what's this tell me to do? It says just to sum over all of the x's. And so I need to sum over all the x's. So x could be 0, 1, or 2. I just sum over those to get the 9/16. So that's what this is telling me to do right here. Sum over the x's to get fy of y. That's fy for y equals 0. If I want fy for y equals 1, I add these two up and get 3/8. And then I add this one up and get 1/16. All of these things together are fy of y. A second ago I said that was fy of y. That's part of it, but it's all those together. To get the marginal for x, fx of x, I sum over the y's. So this is sum over the y's of the joint distribution. So I get the same numbers again, 9/16, 3/8, and 1/16. And these numbers down here are fx of x. Well, it's been about 1 hour and 10 minutes. I'm not done with joint distributions now, but I'm going to end part 1 of this video here and pick it up in the next video. So, see you soon.